Welcome on this beautiful morning, and today we're going to examine complexity from a real-world problem. Let's say we want to apply our knowledge of artificial intelligence code, and we have now quite a variety of options. If you use a word embedding, a sentence embedding, if you're going for a graph theory, if you do some graph embedding, but how you apply it and how you fine-tune the methodology and the code that you already know. And I want to show you from an actual project that I have, and this is the conference on the future of Europe. I want to write a contribution. And you're going to ask me, okay, but how can AI help in a complex topological construct, like the future of something? Well, easy. I need a dataset. We always start with a dataset. And my dataset is 5 years back and 5 years in the future of already signed European R&D projects. And I have about 34,000 projects. And these are my data. Now, on to the options that I have. We always have to know if we apply a specific code sequence to a problem, is it the right order? Is it the right magnitude? Has it the right complexity to give us insight into the data? And I want to show you the way I approach it. Here, I take 3 options, and I will show you the benefits and the drawbacks of those options. The first is a very simple one. You know it, it's a word distance problem. You just have to know Python. You take all the sentences, and you're looking for specific words. I want to write about the city of the future, the urban structure of the future, the civilization of the future. A simple problem. So I have some search words: city, urban, megacity, public transport, smart energy, combination with mobility. What does it mean for health, for inclusion? How does data and information and communication technology influence urban life? What about the air quality, the water? What about education, culture, food, waste? All these problems that you encounter, for example, in the urban space, how do they interlink? How can I make sure, if I approach this topic, that I understand the complexity of this topic and how those topics interlink? And this is why I'm going to apply today the first option, the word distance option, a classical graph theory. If you want, you have a sentence. The sentence consists of words, and now you take ego graphs. So what you do is very simple. You have at first to construct a graph. And the graph is based on the words in the sentence. Let's say in the middle of the sentence you have the word city. And around city you construct a certain window to the left side and the right side. You count 3 words to the left and 3 words to the right. And then you say, hey, what are all the words within this window? Is, for example, mobility twice? Or is there mobility 3 times? Or what are the words that are connected within this word to my target word city? And then you construct it for all the words, for all the different variations. This is simple Python programming. There's nothing special to it. And you get a graph structure. And when you have a graph structure, you can simply visualize the content. And this is what I'm going to show you today. Second option, of course, here is, if you want to increase the complexity, is to apply some TensorFlow to knowledge, and the method we're going to use is word2vec, the very old classical word2vec. Remember, king, queen, simple. But it gives us something in advance, given a simple linear word distance learning. So you train it on the sentences, you define the vocabulary, you know word2vec. You can have either the glove or you'd go for some other implications. I prefer to do my own training on word2vec on my own data set, and I want to have a very specific targeted representation of my data. Here, I don't want to have some pre-trained knowledge, body of knowledge that I want to apply. I do own the training on those sentences. Remember, I have about 34,000 projects, so I have about 500,000 sentences, maybe even if you expand it close to 1,000,000 sentences. So 1,000,000 sentences already sufficient to apply some TensorFlow application for Word2Vec. So, and I'm now curious, what are my topological distances if you have a shallow neural network and now you decide on the topological vicinities of one word to the other words and so on. And of course, the third part of this will be we embed whole sentences. Here we have focused on the words. Now we embed our sentences and we detect thematic cluster. Remember, we have 34,000 projects. I don't want to read 34,000 projects or maybe 50,000 projects just to find out what is the current research or the research that has already been signed and will be conducted in the next 3, 4, 5 years. So to do this, third option, we apply SBERT, the sentence transformer methodology, and or any other BERT-based model if you want, Roberta or whatever. And we have code demonstration. I will show you how to use the code to find a solution to this insight that we are looking for. What is the European research currently performed on the city of the future for the conference, The Future of Europe? To understand a little bit why we do this, let me show you another presentation here and now in the dimensionality of the complexity. The word distance is calculated in 2 dimensions. You have a sentence. A sentence consists of words, and you simply count, hey, in this sentence I have word A, B, C, D, and the distance of the word from the first word to the third word is a certain distance, and you can write the frequency of this distance also. And then if you have all the data, you can fold for each and every word and for each and every sentence is in a 3-dimensional visualization, and I will show you how this looks like today. Next time we're gonna have a Word2Vec on a TensorFlow calculation, and here we already calculate the neural network, this shallow neural network where we take the weights of the hidden layer and have the assumption that this is somehow an encoding after the training of the semantic information we are looking for in 128 dimension. And I choose 128 dimension because this is, if you have 500,000 sentences, this is easily done on Colab, on the Google Cloud, in the free version, because there we have only 12 GB of RAM available for our GPU, and 128 dimension is exactly the maximal amount of dimension I can calculate for free on Colab. If you have your own cloud-based infrastructure, well, of course, you can go 256 or go crazy, whatever. And here, now, the third option, sentence transformer methodology, the BERT methodology. Normally in the pre-trained model, and we're going to use here a pre-trained model to have some transfer learning. It is calculated in 768 dimensional topological spaces, where we will construct then our dimensionality reduction algorithm with UMAP or dense map. We will reduce the dimension, we apply some clustering algorithm, as you already know, as I already have shown you in the video before. And we're going to find here another insight. Another topic is to understand what is the insight of the first methodology. Does it provide some input for the insight when I apply the second methodology? And what I will get now in the final result on step 3, if I apply a complex transformer model, sentence transformer model, what will be the insight I will get from this? Before I will write my own contribution, I will understand what is available, how it is calculated, how it is interlinked, the topics from urban life, quality, water, culture, education, food, waste, mobility, transport, living. So, here we go. Today, the classical graph theory. What information am I looking to tackle these problems? Yeah, very simple standard Python programming in neurolinguistic programming is I take the bigrams. I look at all the bigrams. This means the words that are standing right next to each other in a sentence. For example, I have here my focus. I decided on city and urban as my two key target words. And I say, hey, find me all the bigrams in the sentences in all the 34,000 projects. Take those sentences where I have either the word city or the word urban in it. And you notice here, I lose all the other sentences that might have a contribution to city and urban. But since I'm operating here in a two-dimensional search scheme, I only have city and urban. So be aware of the limitation of this topic. And in those sentences, I apply a simple bigram search. I look in those sentences, what are the top bigrams? What is the frequency of those top bigrams? And as you can see here, it's very simple Python programming. I don't need to show you the code. You know that already. I have here now the top bigrams of my 34,000 projects. So first, urban areas. Well, clear. Smart city. Well, of course, you want a smart city. Urban and mobility. Urban and environments. Nice indication what I'm looking for. Sustainable. Climate change. Wow. Number 6 is already climate change in a city and urban context. Air. Transport in the urban rural area. European cities, of course. Air pollution. Context. Urban centers. Urban water. Governance. Design. Regeneration. Air quality. Air mobility. Urban spaces. So you see here, I get a good idea just looking at the bigrams and the frequency of the bigrams. What are the major topics people are interested in and currently are doing some research on? Health, the freight, the logistic, the transformation, the data structure, the population growth, transport, food. And you will say, well, okay, these are just the bigrams. This means the words that are already standing right next to each other. But what about there is a word in between, and I'm looking for exactly this? Well, now we extend the ideas of bigrams. We open up the linearity to a higher distance. And as you can see here now, I have here a presentation where I have a source, special word, and I have a target word. So within these sentences, with all the words in one sentence, I run through all the words in the sentence and say, okay, first word, first sentence. Let's say it is cities. And the second word in the first sentence is urban. So I have a source and a target, A and B word. And then I count how often I have exactly within a window of words, because let's say my sentence has 50 words. So I have a window of 20 words to the right and 20 words to the left. And I look at all the words in the window starting from my target word. And I calculate how many words apart are those words. So it's not a bigram, words that stand right next to each other, but these are the words within one sentence. The sentence is the boundary condition, if you want, on the system we're analyzing. And for all the 500,000 sentences, I just check the weight. And the weight is simple, the number of appearances of a typical duplex source and target word within a sentence. So what we get is, of course, identities, city and urban. Well, of course. Cities and city, singular and plural. Well, of course. Now it gets interesting. On position number 3, we find social. Social in urban and city R&D. Interesting. Develop. Knowledge. Data. Seems to... Oh, sorry. No, back. This happens if you touch the keyboard. Where have I been? Data. City and urban. Well, of course. sustainable, European, local, design urban spaces. Interesting. So as you can see here, in addition to your frequency of your diagrams, you get another very simple insight into the topics that are researched here. Environmental, mobility, the services, the urban services, citizens, health, networks, network structure, strategy, impacts, political dimensions, mobility, climate change, and again, water. And now that you have all those source nodes and target nodes, and you know the weights, well, when you know what it is a graph, a very simple graph structure. So you have two-dimensional net on edges, manifolds. Now what we do is we fold it and we get a three-dimensional network visualization. So here you can see I have just a top-down meta view. I say, okay, I want to have the ego nodes within this graph. So ego means I have here, let's say, my node urban, and I want to see here for one step, for one elongation the words. And if, let's say, European environmental would have a link too, if those have a link within, if they are directly connected to urban. And as you can see here, and I do this for the node urban and the node city. And you can see already here a topological structure appears. Because here you have from urban all the topics, R&D topics that have a direct link to urban. And here, if you have the node city, you have here those two rays, if you want, that have only a topological connection to the word city. So future, city, and the city science, if you want. Urban, you have here the problem of waste, the problem of water, the water of networks, plural, strategy, design, political, infrastructure, production, impacts, health, and social again. And you see here I try to indicate the width of the edge as the importance of the edge. So you see here very clear social, urban. This is a topic within urban that is studied quite a lot. And you see here within city, interesting, you do not have such singular topics only connected to this node. But now the main point of interest I need for my work is, what about the interconnects? City and urban should be, in my idea, similar wordings. City and innovation and urban, they are interconnected. Mobility, you have a link for mobility from the node mobility, city and urban. And here you go on. And you see here in this area here, between city and urban, here are all the edges that are interlinked, and those nodes are my focal points because I want to find out about some insight. And if you want, this is the insight I'm looking for. Mobility, innovation, energy, sustainable, smart cities, European. In my search raster of city and urban, I find this common search parameter. Of course, you can say, I just want to increase the complexity. And if I have energy, I want to know now about energy too. And energy now becomes one of my ego nodes in my graph from my word distance matrix. So you can go on, but I want to show you that if you increase the complexity, you can, of course, increase the boundary condition, the thresholds. And I want to show you here, if the data becomes a little bit more complex, it is very nice to start with a three-dimensional representation. And this is the same data as in the picture above, but now it's not a picture, but it is a three-dimensional interactive representation you can play around with. So again, here you have urban, city, you have the two rays, future, science, you have your urban single links here, and you have your interlink between city and urban here. And you can look at it from these different perspectives. You can zoom in, you can have, you can have a look at it, whatever. Now you say, well, what for? Well, easy. If you increase now the number of edges you're interested in by a factor of 2, you get new edges, you get new nodes, you get new insight into the topic. Let me show this here. Oops. What is the best way to present this data to you? Well, yeah. Zach, come on. Don't play around with me. So, okay, here, urban, and here we have a spectrum of singular urban topics. City, we have here arrays coming out from city, and here is the area that I'm interested in between urban and city. What are the interlinks that are common to those target words? And as you can see here, I applied another trick, if you want. I want to get another level, another density of information. I want to increase it. And I simply substitute. You remember at first we were looking for the bigrams. Now I took the first 100 bigrams in my sentences, and I substituted, if there was in a sentence the word urban right next to mobility, I now put in, instead of 2 words, 1 bigram, and for the top 100 bigrams I performed this operation for all the sentences. So now I have a new word, if you want, urban underscore mobility, where I see, okay, within the context of urban mobility is here the topic. You have here smart city, and you can choose whatever you like. I just made the top 100 bigrams within all the sentences. And you see you get another layer of data here. And I have here now 100 edges. If you have, for example, a complexity of 500 edges, you will see that operating with bigrams or maybe even trigrams significantly reduces the complexity of the visualization, helps you to understand what you are looking for. So city here, and we have now some single rays to the platform technology, the life, the researchers, innovation, science, digital, and the future. Future and digital we already know. This is one of the very simple representation. And you have your urban spectrum right here. And now we have some new insights. We have energy, mobility, the traffic itself, the community, the waste, the economic perspective, the modeling, the smart city, and so on. So you see here, simply by counting the distance of words, we already get quite some insight and we can have a nice visualization. And if you have a client that says, hey, what's the content on my specific topic that I'm interested in of 50,000 projects, you can here very easily make a very nice presentation without applying AI. Since, hey, the session is called How the Heck to Do Your Own AI. This is just the starting point, because now, if I'm interested in the area of urban and city and the future of those, the research that is done, I can now take here, let's say, transport, and define it as a new interesting cluster I want to explore. The innovation system I want to explore, the energy dimension of this problem. I want to have the mobility aspect, the health aspect, the social aspect, all the data networks for a smart city. What is the research on the data structure? What is performed currently? What are all the university in Europe are researching on the smart city? What are the topics? What are the technologies they apply? So now the next step here is I'm gonna dive exactly in those words, in those semantic meanings. But now I know on if you want a top level or you're looking at the medium level, or even if you're looking for outliers, you can build a graph and easily visually identify it. And if you want to know the next video, because this video is already much too long, 24 minutes, heaven's sake, I'm going to show you how to take the insight here from a simple graph from word distances and build this insight into a word-to-vec representation, a 128-dimensional neural network, a shallow neural network. And I want to show you what we will get in the next video. And you will get a representation like this. As I told you, I have another time here my node urban and city. Now all these cohorts, if you want, citizen, water, pollution, energy, air, transport. I have now run a TensorFlow neural network learning, and Yeah, the neural network learned the semantic context of each and every word in each and every sentences of 500,000 sentences. And you can see here that somehow we get a very nice idea how those words and the semantic meaning of those words in the sentences. So we increase the complexity from a single two-dimensional word distance approach. We can go now to a neural network interpretation. We do all the learning, no pre-training here, because I want to know exactly on this data set that I have the context and not on some encyclopedian knowledge base. This is my data, this is my knowledge base, and I want to connect all the connects that exist between different topics I choose to have a closer investigation on. And I will show you this in the next video. And now it is already over 25 minutes, so I say thank you. This is what we're gonna code in the next session. And now next time we're really gonna use some code, because there is an artificial intelligence network, and I'm gonna show you how easy it is to get those insights. And of course, if you want to increase the complexity and instead of 10 nodes, you have 20 or 50 nodes, it is always nice to have a three-dimensional representation you can play around and show your client on a big screen that he also understands the interlinks between different topics, or for a politician to show him that currently they are in a state A and the projections show that it needs to be in a state B, or whatever you are arguing. So thanks a lot for this session, and I see you in the next one.